Okay, there's a small little bit about experimental determination of rate, and then we're going to go and look at exactly the mechanism of reactions. So how will you determine experimentally in the laboratory how fast your reaction rate is going? So the answer is it depends. It depends on the properties of the reactants and their products to determine how you're going to measure it. So let's look at some examples. One that is very hard to do is through color change. Okay, we are very with our eyes like, oh, it's blue, oh, it's green, oh, it's purple, oh, we don't know. Okay, but you can get a color meter or a spectrophotometer, and then what happens is you do the experiment, and the experiment changes color, and you look at the color through the spectrophotometer or the color meter. And so this is the light source, which would be like your whatever to make the rays of light. We focus the rays of light, we put them through a prism, and then the prism splits the light, but we choose which color we want to go through here. So say for instance here, this one's gone, only yellow gone through here. And then here in a special container you put in your chemical reaction, and then you check how much of the incident light is transmitted, and then the digital meter reads it. Okay, so like, I've never seen this in action, but it exists, and this is the way you can use a color meter, by putting specially colored light through the sample and seeing how much comes out, how much is transmitted, how much is absorbed, and taking a reading. So that's one option. This is far more happens far more often, that you see this in your experiments. Okay, there's either a volume or a mass change. So say for instance I mix in here vinegar and bicarb. You know the vinegar and bicarb is going to produce carbon dioxide. It's going to bubble out here, and if you connect this to a proper gas syringe, the plunger of the syringe will be moving backwards as more and more gas comes out. So you can say at 1 second take the reading, at 2 seconds, at 3 seconds, at 4 seconds you take a reading on the gas syringe to see how much gas has come out in per unit time. Okay, so here's another way of doing it, a more primitive way if you don't have a gas syringe. You know those measuring cylinders you have in the lab, and they've got all the markings? You fill up the measuring cylinder with water, you put your reaction in here, and then you let the reaction go to completion in here, and the piping comes out, and then it displaces the water, and one of you is reading the markings off the measuring cylinder. So this is if you've got a proper gas syringe. This is exactly the same concept, but you're using the displacement of water. As it pushes the water out of this measuring cylinder, you can take the readings off there. So this is another option for measuring the volume of gas. Your other option, yep, it's in the picture the next picture, is the loss of mass as a gas escape. So now we don't think of the air having a mass, we don't think of carbon dioxide having a mass, but the carbon dioxide obviously has a mass because we do calculations with it all the time. So in an open system, okay, these two are closed systems because there's no way for the gas to go. In an open system, this is an open system. Here they've got hydrochloric acid and probably calcium carbonate, and the acid is going to react with the calcium carbonate and produce carbon dioxide gas and a salt and water. In this reaction, on your scale, you take the reading on the scale before you start, then you drop the metal chips, the calcium carbonate chips in there, and this cotton will plug. This will let gas escape, but it won't let water escape. So even if this bubbles ferociously and the bubbles come to the top of the container, the cotton wool will trap the moisture and only let the gas out. So all that we are left with is all the change in mass that we get is due to the gas escaping. Okay, so you have to use your stopwatch with it. So then it's 30 seconds. You say, for instance, before you drop these rock chips in there, you take the reading on the scale. Then you drop the rock chips in, you take a reading. 30 seconds, another reading. A minute, another reading. And so then as the gas escapes, this is going to get lighter and lighter and lighter. And then you can plot a graph and you can take the reaction rate off the graph. Another way, because all reactions are usually exothermic or endothermic, is you can measure the temperature change with a thermometer. So you need a stopwatch. You put your thermometer in the reaction mix. You make sure your reaction mix is in something that doesn't let heat escape. So they often use those throwaway coffee mugs, those styrofoam ones. You know, the ones that are like polystyrene, the squishy ones. Heat doesn't go out of those easily. So this keeps the temperature, stops the heat escaping to the surroundings. So then you measure on your thermometer, is it getting colder or is it getting hotter as time passes? Then you can measure the pH. What you could do is you could be putting in universal indicator paper every 30 seconds to see how the pH is changing, or you can spend a couple of $1,000 and you can get a pH meter, and the pH meter will give you a reading, a very precise reading every 30 seconds. This is much more qualitative. This is quantitative because we get a number out of it. So for instance, if we had a neutralization reaction going on in here and we started with the base, you would find that it was very high pH, and by the end of it, it goes down to pH 7. So this is another way of measuring rate of reaction. The last one, yes, I think it's the last one, is turbidity. Okay, sorry, I left you on that other slide for too long, but this slide is very slow because of the animation. So when you form a precipitate, if the product is insoluble in the solvent that is present in the reaction, so obviously now you can have like ethanol, alcohol as a solvent instead of water, so that's why this is being imprecise. So if the product of the reaction cannot dissolve in the solvent, then the solution is going to become cloudy, which we also call turbidity, and this is due to the formation of a precipitate. So like for instance here, you can see he's squirting in a colorless liquid. This was a colorless liquid, and when the two meet, a precipitate forms and it becomes turbid or cloudy. Over here as well, the turbidity is increasing till you can't see through it. So you can use this to measure rate of reaction. If you need to know what's going to be a precipitate, you have this solubility table from last year, and so things that are soluble are, you know, all the soluble things, and then you know the insoluble things, so then you can figure out turbidity. Okay, this reaction, this turbidity thing, is used with this reaction. The sodium thiosulfate plus sulfuric acid goes to sodium sulfate, elemental sulfur, sulfur dioxide, and water. So sulfur dioxide is bad for you. You should probably do this in a fume hood. But what you do is you get a piece of paper and you draw a cross on the piece of paper, and this reaction is not that fast. Okay, so you mix the sodium thiosulfate and the sulfuric acid, and you see how long it takes till the cross disappears. And the cross is disappearing because the sulfur is precipitating out, and they've drawn this as yellow, but it's like a dirty white color. And then you say the reaction is complete when the cross disappears. So you repeat this reaction with different concentrations, for instance, of the acid, and you say, okay, it took 30 seconds for the cross to disappear when the acid was concentrated, and it took 5 minutes for the cross to disappear when the acid was dilute. And this is where we'll stop. Oh, while we're here, there's also the iodine clock reaction works like this. I sent you a video of the iodine clock reaction, or you can Google the iodine clock reaction, and you'll see this is also a use of turbidity.